First of all, warm greetings to each and every one of you. My name is Raghav Sharma, and I'm present here to present in front of all of you this work on a named entity recognition system for the biomedical domain. This paper has been authored by myself, Mr. Deependra Singh, and Mrs. Raksha Sharma. So, in recent times, you will see that there has been a significant increase in the rate at which the information is being published in the domain of medical science, with the Medline database growing at the rate of more than 500,000 new citations every year. This makes information extraction in this field an essential task. In this paper, we have worked on named entity recognition, which is a subtask of information extraction that focuses on the identification of named entities present in unstructured text. Entities in the biomedical domain, however, have complex names, which are a combination of alphabets, numbers, and some special characters as well. Often, the same abbreviation or phrase can refer to multiple different identities. So in order to handle these challenges and be able to extract named entities properly, we have experimented with two transformer-based models, namely BioBERT and RoBERTA. But before we move to what approach we have used for this problem, I would suggest that we should have a brief look at the approaches that have been used previously. Some of these approaches are rule-based approaches, which use handcrafted rules and also an exhaustive lexicon, and they use these to identify the named entities in biomedical text. However, these rules and lexicons make the model very data specific. So what happens is that whenever we change the source data, the performance of the model drops significantly. Um, Also, supervised machine learning approaches such as CRFs, HMMs, and SVMs have also been used for this purpose. However, the issue with these is the lack of structured and labeled text in the biomedical domain, and this causes a major hindrance in the performance. This has also led to the rise of unsupervised learning approaches, which focus on corpus statistics and terminologies. In recent times, however, the deep learning techniques have taken over and they have shown good performance and with their end-to-end approach. These models generally use word or character embeddings as input, and several such approaches have been tried. However, transformers have shown superior performance. In this paper also, we have used transformer-based approaches. Now, coming to the BioBERT, Robert, and all these technical models that I have been mentioning so far. So, BioBERT is based on the fact that biomedical text is full of domain-based information for which understanding the knowledge of the biomedical domain is critical. So, BioBERT basically uses the relatively simple architecture of BERT and trains it on an entirely biomedical corpus to ensure that it performs better on biomedical text. Now, moving forward to Roberta. Roberta is also quite similar to BERT, with there being some fundamental differences in, but the training process being completely similar. So Roberta basically uses dynamic masking instead of static masking. This means that it creates a new mask for every iteration, unlike BERT, which does so after 10 iterations. Roberta also ignores the next sentence prediction task, which is used for training BERT. Apart from these, Roberta uses a larger batch size and a bigger vocabulary of 50,000 subwords instead of 30,000 subwords used in BERT. Moving forward to the LAMP optimizer. So the one important part of this is that training transformer-based models takes a lot of time. However, one way to reduce the training time is to increase the batch size. What happens when we increase the batch size with direct optimization is that it reduces the performance significantly. LAMP is a layer-wise adaptive large batch training optimizer, which uses Adams optimizer with weight decay for training. So this basically reduces the training time without really affecting the performance of the model. Moving forward to the experiment, our experiment is basically divided into parts where we do the pre-training and fine-tuning. In pre-training, we pre-train the BioBERT and with both the BERT and Roberta approaches. And at the same time, we also compare the loss which is attained using the Adams and Lamb optimizer. Moving forward to the fine tuning, we fine tune the model for named entity recognition in the biomedical domain only, and then we then we compare the performance of the models of both the BioBot and Roberta models after they are trained on the biomedical corpus. comparing the results. When we analyze the performance of the Adam and Lamb optimizer, we see that the F score is basically the same with negligible difference being between the F scores with Adam and Lamb optimizers. However, the loss that we attain after using the Lamb optimizer is significantly lesser than what we attained with the Adams optimizer. This shows that a Lamb optimizer has performed superior to the Adams optimizer. Also, when we compare the performance of Bert and Roberta on the biomedical corpus, we find out that Roberta has significantly improved the F score on all the biomedical data sets that we have used in this experiment. To summarize, we have analyzed that the BioBert shows superior performance in biomedical domain due to its domain-based training, whereas the structure of BioBert is more suitable for the task. We combine these strong features by using the structure of Roberta with the domain-specific training of BioBert to get better results. We also compare the loss attained by using LAMB and Adam optimizers and find that the LAMB optimizer is able to achieve much lesser loss. That will be it from my side. I would like to thank all of you for being such a patient audience. Thank you. We are open to questions.
Okay, thank you very much for delivery of the presentation. And if there are any questions, please don't hesitate to ask them.
Yes, yes, I would like to ask if you have any plans, or maybe what area do you see to develop this technology? Your work? Okay.
I'm sorry, Pavel, I could not follow the question. Can you repeat it, please?
Yes, I'm just curious. What area do you think this technology, this work can go in future? How it can be developed?
Okay. So basically, for this, I would like to give you an example. The example is of recent time, the COVID time. So it was widely seen that during the COVID time, a lot of research was being done around the globe, and a lot of new information was coming in every day, every hour. So basically, what happens is that if medical workers, doctors and researchers have access to this data easily, have easy access and quick access to this data and relevant data, the data that they want, this will basically help us in advancing the research first of all. And if this works out fine, and if we are able to actually actually advance it to a very good level, we can also help doctors to actually take advantage of this research very quickly and be able to apply that research in real life to patients and help them cure very easily.
Okay, thank you.